To round out this week, I would like to talk a little bit about fractals obtained in a different way than all the ones we've seen thus far. Thus far, every kind of example we've seen of a fractal has been something obtained by some kind of a recursive mathematical process. In fact, an exact process in the sense that there are certain rules for generating it. You follow those rules precisely. There are no choices to be made, no randomness in the construction. You end up with this elaborate, rather complicated kind of object, but it's all been by an exact and, in some sense, very simple process. So now I want to look at fractals occurring somehow naturally, maybe not really in a mathematical way, and then a little bit at fractals occurring by some kind of simulated process, some engineering or manufacturing process. Now, I want to ask that in addition to what you listen to me spout off about here, that you also look in the materials for the course for a couple of handouts and read through those. One of those is called Fractals in Nature and Simulations. The other one is called Fractals Created by Diffusion Limited Aggregation. They are not long handouts. I think they're just 2 or 3 pages apiece. Now, the idea here is that things that look like these fractals that we've created also seem to occur quite naturally. In fact, this is why the field of study called fractals in mathematics is so appealing and seems so important and central in mathematics already. That's because it allows us to come up with things that have this very naturalistic appearance. So let's come at it from the other direction now. Let's look at things in nature and see how they seem to have fractal properties. That is to say, they're fractured or irregular. They seem to have maybe the same sort of appearance at every scale. For example, look at that photograph of clouds. Now, what's the scale there? Are we looking at a cloud that's a mile across, a half a mile, just a few hundred yards? It's very hard to say, right? Because that's an aspect of clouds. That's something we know about clouds. They seem to just have this same sort of appearance, no matter what scale we're talking about. If you zoom in on a cloud, what does it look like? It still looks like a cloud, right? It doesn't have any special kind of features, unlike, say, a human body, where you say, well, when you zoom in on some part of it, well, then it doesn't look like the whole thing anymore. You're looking at a hand, say, or a finger. But zooming in on a cloud, you just get a cloud. You also sometimes see what you would regard as fractal features when you look at vegetation. So here I'm looking at a particular kind of broccoli that's called Romanesco. And this has it in a very striking way. So we see these rather intricate-looking features in the flowers of the broccoli, the actual edible part of the broccoli. And when we look at more closely at them, it seems like they're just smaller versions of the whole thing. So that's certainly a fractal appearance. Of course, it also looks very fractured and irregular. Let me take another example. Let me show you some watersheds. So these are all maps or drawings of various watersheds. That is to say, showing the branching pattern or the combining pattern of all the little flows of water that feed into a larger flow of water. Okay? Now, the first thing I want to observe about this is, roughly speaking, all of them have the same sort of appearance. They're not the exact same shape, but they all sort of have this same sort of appearance. You'd look at each one and say, oh yeah, that looks like the pattern of water collecting in a watershed and somehow flowing downstream and then finally feeding out into something else, maybe a bigger river or a bigger body of water like a lake or an ocean. But what I want to note is, despite the fact that these all have a very similar appearance, they are at wildly different scales, wildly different. Let me tell you what they are. So when we look at A, which I want to look at it in the next slide. This is showing the watershed of the Nashua River. So what you're looking at there is about a 538 square mile area. It's a pretty good chunk of territory straddling the border between Massachusetts and New Hampshire. And picture B, I can now tell you, is the watershed of a small brook in Connecticut. So those little streams feeding into this brook are really tiny little streams, okay? This picture is only 7 miles wide, so it's not nearly as big as what we're looking at in A. And then finally C, what is that? Well, we're not quite seeing all the detail that we could there, but there's plenty of detail that we could see there, because what we're looking at there is in fact the watershed of the Mississippi River. Once I tell you that, you might begin to even recognize certain shapes. If you know what the western boundary of the state of Illinois looks like, for example, you can actually observe it in here. The main stream there, so to speak, is the Mississippi River. At the top right, that's actually the Ohio River coming in. The very long one that's coming in from the upper left is the Missouri River. And as we look at this, we're not seeing much of the fine detail that would perhaps make it look even more like pictures A and B. We're not seeing the Walhanding River. We're not seeing the Mohican River. We're not seeing the Clear Fork that feeds into the Mohican River in Richland County. But the point of all this is not what are the details and what are the names of all these things. The point is somehow watersheds always look the same. In a certain sense, water drainage patterns always come out looking the same, and they look the same at all scales. Now, you might say, well, these objects we've just been looking at, these watersheds, if I may go back to them, don't look a lot like those other fractals that we've constructed thus far, like the Sierpinski gasket, like the Koch curve. And that's in part because those other constructions of the mathematical fractals thus far have always had a little bit too much regularity in the sense of symmetry. So what we're going to do is to think about a way in which we could introduce one more mathematical idea, which is the idea of randomness. Okay, so imagine that we begin with a line segment, the same way that we begin with one of the edges of the triangle in beginning the Koch curve. And now what we're going to do, as we did in the construction of the Koch curve, is we're going to take that line segment and replace it by this broken pattern of 4 line segments. However, we're going to add one other idea to this, namely, we're actually going to take a coin. Now I'm jingling a coin here. Here's some coins that I've taken out of my pocket, and I can take one of those, and you can't see me doing this, but I'm flipping the coin, and I'm tossing it, and I'm putting it down and seeing if it came up heads or tails. It happened to come up heads. So what that means is I'm going to take my line segment, I'm going to replace it by the picture shown at the top, which seems to have a point coming out upward. If it had come out tails, then I would have replaced it by the point going downward. Now, in either case, I have a pattern consisting of 4 line segments, and now I can flip the coin 4 times. And for each one, I can do this replacement, either pointing up or pointing down replacement, right? So I'm always going to follow this rule. If it lands heads, I'm going to replace the edge by one thing. If it lands tails, I'm going to replace it by another. And I did that once. I could do it many times. At one time I tried this, and here's what it looked like at an early stage. Here's what it looked like at a later stage. I hope you're thinking, ooh, that's even better than those ones we had earlier. So if I don't just use the idea of recursion, but also add to this the idea of randomness, then I can get to things that look more and more like natural things. This begins to look, I would think, somewhat like a coastline. Finally, I want to talk about simulations. One kind of simulation that I don't have a slide here to show you is in that handout referred to earlier. Let me go way back. Remind you, there was a handout called Fractals Created by Diffusion Limited Aggregation. And there we're talking about a process which can be done either simulated in the computer, or you can actually try this out with natural objects, in which you try to grow a crystal by letting it just naturally accrete molecules or accrete particles. And when you do that, you get a very interesting kind of shape. It doesn't give you a rather mild-looking blob. It tends to give you something that has very long tendrils on it. So I'd like you to take a look at that. As another example, I want to show you that here is an actual U.S. patent for an antenna. And this is an antenna that's deliberately been made in a fractal design. That is to say, it's been made in such a way that it has this self-similar appearance. If you take one of the quarters here of the antenna, it looks like just a smaller version of the whole antenna. It's deliberately been made to have these fractal features. Now, why would you do this? Okay, well, using this sort of design actually accomplishes two things at once. First of all, it manages to fit a long antenna into a small space, which is what you want to do in the cell phone. And also, because of the fractal nature, it turns out one can work out the fact that it actually operates over a very wide band of frequencies.